All right, so by the end of this lesson, you'll be able to describe the pattern of the magnetic field in and around a permanent magnet, describe how ferromagnetic materials become magnetized, describe how some magnets are stronger than other magnets, describe how the magnetic poles of the Earth are oriented, and describe why behind what you observed in a lab. Okay? Give that one a shot. Tell your neighbor what you think. Okay, hopefully you have eliminated choices A and D. Okay, so it's either B or C because your magnetic field goes out of north into south. Okay, so that's one factoid. The second factoid is magnetic field lines produce full loops. So the correct answer is B. Okay, so outside the magnet, your compass pointed out of north and pointed into south. It continues to make a whole loop. So inside the magnet, it goes from south to north, but outside the magnet, it goes from north to south. Okay, so it is really important to make a distinction. Are we talking about inside the magnet or are we talking about outside the magnet? Okay, so here are, this is a cool, please don't drop this. Um, so this is like three-dimensional, um, so you can like shake it up a little bit. It's kind of like a snow glow, but this is magnetic stuff in like a, it's not water. It's a little thicker than water. I'm gonna guess glycerin, but you can try that out. This, just a heads up, this guy is foam that could pop out. It should be fine, but just beware of that. Okay, so out of north into south. Good with that? Creates a whole loop. Okay, so electric charges versus magnetic poles, they are different. They have similar characteristics, like opposites attract, likes repel, but um, so so we would say we were not going to say that magnets are charged. We're going to say that magnets are magnetized. Okay, don't use the word charge because that we're going to leave that for positive and negative charges. This has, when we rub a nail, it becomes magnetized. Okay. It can, yeah, it becomes magnetized. It depends on the metal, and we'll talk about that here in a little bit. Okay. So one big distinction between these two, you can never have a north and a south. Sorry, just an independent north. We have not yet discovered a monopole, a monomagnetic pole. We can have just a positive by itself. That's totally fine. But north and south are always coupled together. Can't just have a north pole. There's got to be a south paired with it. Okay? Give that one a shot. Tell your neighbor.
Remember, it's stuck. They are.
What do I have? What do I have? Is this it?
Probably.
Isn't that outlet?
Yeah.
Okay, correct answer is D. Okay, not all metals, copper, aluminum, they don't stick to magnets. Okay, a lot of, so your ferromagnetic materials, elements are iron, cobalt, and nickel are your three magnetic elements. Okay, known as ferromagnetic. The ferro comes from the Latin word of iron. Okay, that's where we get the Fe from. Okay, so what things can repel? A magnet can repel what objects? Correct answer is only other magnets. So when you had your when you have your rubbed and your unrubbed nails, the unrubbed nails would always attract. You wouldn't get repulsion unless you had two rubbed nails, or at least you should have. If your unrubbed nail repelled, I apologize. I did not clean it well enough. Okay. All right. So, um, why are these three elements magnetic? So it turns out that a very fundamental level, moving charged particles create a magnetic field. Um, and so in chemistry, I don't know if you learned this, but electrons have spins. That spinning creates a magnetic field, but electrons usually are paired with an opposite spinning electron. So one's spinning up, the other one's spinning down. Those two magnetic fields that they produce cancel each other out. But these three have valence electrons that are unpaired in their spinning. And so they have like 3, 4, 5 valence electrons that are all spinning the same way, not canceling, and their magnetic fields are not being canceled out. So when these form crystals, these crystals are called domains, and they are magnetic. Okay, and so these magnetic crystals have a certain magnetic orientation to them, and they're all scattered. Okay, so iron is probably the most uh, the magnetic element that we have exposure to us because steel is made. Iron is one part of the steel ingredient, like it's one of the elements in the steel. And so when you have magnets stick to stuff, it's because of the iron in whatever steel, refrigerators, chair legs, um, faucets. Okay. Um, So to give you an idea of the size of these magnetic crystals, this is 20 micrometers. So this is like red blood cells. A skin cell is about like a skin cell would be about this big. Paramecium, when you go looking at pond water, looking for floaties, single cell organisms, that's like the size. Um, so a paramecium would probably fit across maybe a little, probably about this, across the size of this board to scale there. Good with that? Good. Anybody else? You did? You didn't?
I didn't.
Okay. Okay. So how do you make a magnet? So you stick something, so you have this, we'll say a piece of iron that magnetic crystals, its domains are randomly scattered. Okay, and then you stick it in some external magnetic field, and that causes some of those domains to align in the magnetic field that's being, this external magnetic field. And so as the strength of the magnetic field increases, or the time at which this piece of iron is in the magnetic field, it's going to cause these domains to start to line up. And that's how something becomes magnetized. Okay. People sometimes cans, like soup cans, can become magnetized if they sit in your pantry for a really long time due to the Earth's magnetic field slightly magnetized. Okay, the Earth's magnetic field is not very strong, but given enough time, you can get things to do stuff. Okay, but that's how you create a magnet. So give that one a shot. Thank you. Or what made out of? Uh, it needs to have iron, nickel, cobalt.
So like how do you like a nail like unmagnetize it? How do you get like a permanent?
Um, guessing. I'm guessing most magnets that are like these magnets, I can unmagnetize them pretty easily. They're pretty not permanent, but permanent magnets are, they don't look very metallic. They look like, uh, so my guess is they, in making them, at some point there was a liquid form, whether it's melted or something, and then they stick it in a magnetic field in the melted form. Everything shifts, and then when it solidifies, it's like set. Okay. All right. Tell your neighbor the answer to this question. Okay. Correct answer is B. So the magnetic field from this magnet goes out of north into south, right? The nail finds itself in this magnetic field. Okay. So the domains, the magnetic crystals in the nail line up to agree, some of them do, to agree with this external magnetic field. Okay, so this then now becomes the North Pole. This is the South Pole. This actually causes the magnetic fields to get bigger, get stronger, because now this nail has been slightly magnetized. You all right with that? And the magnetic field lines still agree. They still form loops. Good with that? Okay, so here's how rubbing a nail magnetizes a nail. So in the nail, you have these magnetic crystals, these domains. And I'm going to say these domains, they can pivot, but they cannot migrate. Okay, they just can like do this. Okay? So when the north pole of the magnet is here, the domains in the nail have pivoted so that they're doing that. Does that make sense? South pole's like, ooh, okay. And as you rub the nail, you bring that over. These crystals are like, ooh, 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 as you drag that across. Okay. Causing the nail, I'm going to make these big, hopefully big enough you can see them. These magnetic crystals lined up like this. So that this then becomes the South Pole, and this is the North Pole of the magnet when rubbed like that. How does that sit with you? Okay, so the domains, the crystals just rotate, they don't migrate. Good with that? Is that okay? Good there. Okay, for our video viewing audience. Ooh, get it, get it, get it. So there's a magnet in there. 3-dimensional. Pretty cool. We just got this.
Can I see it again?
It's like a new toy.
I want to play with it.
They don't let them back. What is it?
Okay. So, see if you can figure this one out. Thumbs up when you have a guess. Have a conversation. Correct answer is D. Okay. Here's how I think about it. Wherever this ends up has the opposite pole. So this is going to end up being south. This is going to be north. This is going to end up here. So this is going to be north. This is going to be south. Good with that? So if you break a magnet in two, you still get a magnet. It's just weaker. Okay. Which then begs the question, well, how do you get a stronger magnet? Turns out all of these are correct. Okay. So if you have a bigger magnet, that's just more crystals contributing to the total magnetic field, you get a stronger magnet. Okay. If you have a higher percentage of the domains, the magnetic crystals pointing in that same way, that's going to cause a stronger magnet. Okay. If the crystals are more densely packed, then you get a stronger magnet. Have you ever played with a neodymium or rare earth magnet? Like one of the ones that are like really like chrome plated, they're really strong magnets. Like you probably have, you just haven't realized it. But so like these guys, these are like post-it pins. These are neodymium. They look metal, but that's actually just a protective coating. If you scratch that and like scrape that off, it's just chrome plated inside. Just looks like it's kind of a crumbly, uh, charcoalish substance in there. Okay, so all these contribute to a stronger magnet. Good with that? Okay. So, can you ever demagnetize a magnet? So, what if you can scramble the orientation of the crystals, that's going to demagnetize it. Okay? You can do that several different ways. That was not good for magnetization of that magnet. So you hit it, beat it, you can heat it up. Okay, cutting it doesn't scramble them, just makes it weaker.
Why does it say two of these, but it has three options?
Two of A and B, B and C, A and C, two of these. Good? All right, so the last point here. This should have been confusing on the lab. If this wasn't confusing, you missed it completely. Like this should make you go, what? Like compasses should point north, but they pointed towards the south pole of the magnet. That should have been a, huh? Okay. Turns out, so like here's the North Star where Santa Claus lives, North Pole. Okay. That is the magnetic South Pole of the Earth. The geographic North Pole is the magnetic South Pole. Like, why? That's okay. So here's the history behind where it came from. It's better than Ben Franklin just guessing. Wrong. So back in the day, Chinese discovered these naturally occurring magnets called lodestones. So in that time, the main way of transportation long distances was by boat. And they used the sun and the stars to navigate, tell them which direction and stuff. Well, if you have a cloudy day or cloudy night, you're like hosed because you're like, we're sailing in the circles. And so you had to wait for a clear night. Well, the Chinese discovered, I don't know how, by playing, accidentally, hey, if you take one of these lodestones and you float them on a piece of bark, they orientate themselves to point north. Well, that was a huge breakthrough because, like, all of a sudden you got like GPS for the ships. You're like, I know which way north is, even if it's cloudy. And so, if you're the salesperson selling these magical devices, what would you call the point that points north? Hey, this is like the north. This points north. This is the north-seeking pole. This is like this point, and we just shortened it. This is the North Pole, and all a compass is a floating magnet. We just called it the north-seeking. This is the north. It points north. Yeah, right. I mean, no one ever thought, hey, what happens if you bring two compasses together? Like, that's stupid. I need just one for the ship. I don't need two. Because if you brought a secondary compass, opposites attract. Opposite poles attract. And so your compass, the North Pole, what we have labeled the North Pole of that magnet, seeks the opposite magnetic pole. Has to, by the way we named it. So this is the geographic North Pole is the magnetic South Pole. Now, if you take a well, I guess before we do this, where does this come from? The best theory at this point in time, it's a pretty viable theory, is there's convection currents in the molten lava at our core, which has iron in it, and that convection current creates this magnetic field. Okay, turns out that the magnetic north, well, magnetic south, whatever, isn't directly like at the North Pole. It actually is a little bit offset. Okay, so if you ever take an orienteering class where you have to use a compass, there's this idea of true north and magnetic north, which is deviated just a little bit. And it turns out that magnetic pole is actually changing over time, the location of that. Okay, so back when I was in Boy Scouts, the magnetic north was over here, and now it's like somewhere over here. So make sure your map is to date if it's like you're actually trying to use a compass to get somewhere. Cool with that?
How do they know that it's changed? What told them that?
A compass is
Oh,
a compass is pointing like back when they sailed ships a lot, like that was like and if you're going a long distance, that itty bitty difference is gonna like be miles off by the time you get across the ocean. So, yeah, by compasses. So, turns out that if you look at the geological records, like did core samples, then you looked at how the iron pieces of iron had like solidified in like the ocean bottoms and stuff. The north and south poles of the Earth flip flop occasionally. And we're like, what? Like, yeah, over 107 million years, like, yeah, why not? And we're like, and so the follow up question is like, when's the next one gonna be? Like, I don't know. Like, how long does it take? I don't know. Like, does that mean we're gonna die? I'm like, no, probably not. Um, is that gonna mess up electronic devices? I don't think it's gonna happen quick enough to like mess up electronic devices. What I would be concerned with is we're no longer protected as well from the solar winds from the Earth. Sorry, from the sun. So that could be a thing. That would mess with the electronics. But anyway, little fun fact there. All right, last question. Tell your neighbor what you think. I'll give you a quick hint. There is a distinction between the geographic pole and the magnetic pole of the Earth. So make sure you know what I'm asking you to look for, or what I've given you. Correct answer is? Oh dear. So the South Pole of the magnet of the compass will point towards the southern geographic pole, which is the northern magnetic pole. Correct answer B. Read it. Okay. Which geographic direction would the south pole of the floating magnet point? It would point towards the opposite magnetic pole, which is located, so the north magnetic pole is located in the geographic south pole, Curtis.
You said that magnetic north is it getting closer to true north or farther away?
I think it's getting closer. There's geographic. So I think it's. My guess is it's past it.
Is it gonna circle back around?
Hey, I don't know.